So there was a question right before we're starting lecture today on how you would get to the recordings if you missed lecture. And so if you get into your Canvas homepage and then go to Confer Zoom, which I'm actually already in, and now I got you back to the homepage, but click Confer Zoom, the same place that you would have gotten in to come to class. And then up here on the bar, there's a bar up here that says appointment bookings, event recordings. And so if you click on the event recordings, you'll see all the recordings that we've had so far for this semester. And so right now, we're recording it right now. So if you check for that recording, it's not going to come up. But you see that yesterday's recording for June 15th is on here. And so you can just click view recording and that will bring it to you. Okay, so we're continuing on 7.1 in our textbook, which was talking about angles, angle measures. We talked about angles could be measured in degrees, minutes, and seconds. And we were looking at radian measures. We also talked about the arc length of a circle. And so let's just kind of just write down a couple of things that we need to know real quick before we start into the new stuff. Okay, so sorry, so a little sidetrack there, and I will pause sometimes through this to talk. Anyways, so there's a couple things we wanted to review real quick. So if you want to go from degree to radians, you're going to take your, let's say X degrees. So we would take X degrees times the pi over 180 degrees. And if we wanted to go from radians, let's say Y radians, to degrees, you would take the Y, your radian measure, all times 180 degrees all over pi. Okay, so that was one thing that we talked about. And then we also talked about minutes and seconds. And so we talked about 1 minute was equal to 60 minutes, I'm sorry, 1 degree was equal to 60 minutes. And we said that 1 minute equals 60 seconds. And we talked about the 1 dash on top of the number represented the minute, and the 2 dashes on top, kind of right-hand corner of the number, was seconds. Another formula we looked at was your arc length, which we denoted with an S value. S is equal to R times theta. R has to be in radians. And what that arc length is, it's that distance around the circumference of the circle that is being measured. And so, for instance, if I wanted to know what is the measure of this arc in here on this circle, what had to do with our theta, how much our rotation went from our initial side to our terminal side of the ray. And it also had to do with theta. Okay. And so this is the measure of the arc length. Okay, so now we want to look at how would we find the area of a certain piece, like that piece of the pie in there, that circle. How would we find that area?
Professor,
Yes.
where it says R has to be, is that pi radians?
So it has to be in radians and radian measures. And not always does radians have a pi in there. So you might just see 2 radians. But a lot of times when you're converting from degrees to radians, you do have that pi in there.
Okay.
But I'm sorry. And I said R has to be in radians. It should be, theta should have to be in radians.
Okay, theta has to be, okay.
So your angle has to be in radian measure, not degree measure. And so if it's given to us in degree measure, we're going to have to convert it to radian measure.
Okay, thank you.
Yep. Okay, so recall in geometry, we could find the area of a circle. This was equal to, A is equal to the value of pi times the radius squared. So let's kind of think of this with proportions. So we're going to use proportions to find the area of a sector of a circle. Okay, so let's think about this of area all over the circumference. Okay, so we know what the area of a circle is. The area of a circle is pi r squared. All over the circumference of a circle. So our circumference of our circle is 2 pi. So if we reduce this, I'm sorry, it's 2 pi r, right? The circumference of a circle is 2 pi r. And so if we reduce this, notice that your pi's cancel. And you have a radius squared on top and a radius in the denominator. So the one on the bottom cancels one of them on the top. And we get back that we have r over 2.
Professor, what
Yes.
does it say underneath area, underneath the line? I can't really read that.
Oh, yeah. Sorry. Sorry, my cursive gets kind of sloppy, especially on the screen. That
It's
says
okay.
circumference.
Okay, thank you.
Yep. Okay. We're trying to find the area, and I'm not doing this right, I don't think. Yeah. I just want to give you the formula now. Let me come back to this. Let me just give you the formula for now. Sorry. So area of a sector. So area of a sector is equal to 1/2 all times r squared times theta. Where theta is in radian measure. Okay, I'm actually kind of now doing that. Okay, we are trying to find the area of a piece. All over the circumference of that piece or that arc length. So let's take this piece, because we're using proportions here. We know what the area, and maybe I shouldn't have reduced it at first, but that's okay. So we reduce this area over circumference. This is equal to the area of the sector, which we're trying to find, A, all over the arc length. And we talked about above that our arc length was equal to S. But another way to write S, so I'm gonna just rewrite this. So we have R over 2 is equal to the area of our sector, which I'm calling A in this case with the red, all over the arc length. And S, remember, is R times theta. So if I want to solve for capital A there by itself, I could get rid of R times theta on this side of the equation by multiplying both sides of the equation by R theta. And so notice this cancels on the right-hand side, just leaving us with capital A, which we wanted, the area of the sector. This is equal to R theta times R. Well, R times R is R squared theta, all over, because we can think of this as over 1, multiplying fractions, multiply straight across the numerator denominator, 2, which is what I wrote down here, the area of the sector. And I can rewrite it a little different by pulling the 1/2 out front if I want, but we don't have to. Okay, so I wanted to derive that formula for you. And I got kind of caught up in the middle of it, but I remembered how to do it. Okay, so now we got a formula that we can find the area of any sector. So let me pull up an example. Okay, so you have a windshield wiper on your car and you want to figure out when you're doing your windshield, how much of that area is being hit by that windshield? How much of that area of the is being cleaned by that, the windshield wiper? And so we're given some information. So the arm of the blade of the windshield wiper has a total length of 30 inches. So the arm of a blade of a windshield wiper is 30 inches. Then it tells us if the blade is just 24 inches long and the wiper sweeps out 125 degrees. So we're given that the blade itself is 25 inches long. And the angle it sweeps out is 125 degrees. And so we're trying to answer how much
What's the first word?
arm, the arm of the blade.
Oh, okay, thank you.
So how much window area can the blade clean? So how much window? Area can the arm clean? Okay, so let's kind of draw a picture. So you have your windshield wiper, right? And they're normally down. And really only a portion of this windshield wiper has that rubber piece that helps clean the windshield. So let's say that's that rubber piece. Well, it tells me that the whole piece in here is 30 inches. And then it tells me just the blade itself is just 25 inches long.
Did you draw a picture or something? Because nothing is showing up for me.
Nothing showing. I'm starting to draw a picture.
You have to bring down the side menu, like where all the
Oh, yeah. I see it now. Thank you.
Okay. So this is now going to swipe. So you have your windshield wiper, right? And then it's going to start swiping, and it's going to swipe 125 degrees. So if we go up, if we're thinking of this as the X and Y axis, and this is the positive X axis, and we go up, remember, angles are positive if it's going counterclockwise. And so if we go up 125 degrees, when I hit the Y axis right there, that's only 90 degrees. So I'm going to have to go about 35 degrees more than that. And so that's going to hit up here. Because that part of that's gone. Right. And so when this is swiping, it's only hitting this area in here. And there's this little piece in here that's not getting anything at all. That's not being cleaned in there. And so we want to find this area. So how are we going to do that? Well, so notice if we took this whole area, thinking of it that it's sweeping out this whole area of 30 inches, so including this little piece in here that's actually not being cleaned, right? If we took that whole area, so the area of the swipe, if it was 30 inches, but then we need to subtract off a little piece, right? So if we figured out what this little piece in here was, so minus the area of the piece not getting hit. By the blade. Okay, so again, area is equal to 1/2 times the radius. 1/2 r squared times theta. The thing is that our theta has to be in terms of radians. So theta equals 125 degrees, and we need to convert to radians. Okay, so we can do that. We can convert to radians, a degree times pi over 180 degrees. Okay, so I'm going to reduce this a little bit. I noticed that 5 goes into both of those. And so we have 25 pi, and I'm going to reduce some more, and 5 goes in there. No, it doesn't. 36 times. Okay. So I'm going to keep my radians, I'm not going to reduce, as 25 pi over 36. So if I want to get the area of the bigger piece, the whole area, so this one, right, is 1/2 times the radius, which we're given is 30 inches, time 1/2 pi r squared. And then the area of the littler piece, that's 1/2. Well, the radius of that little piece, well, that's 30 inches for the whole thing minus the 25 for this black piece. And so that's just 5 inches. So 5 squared times pi. So the area that we want is equal to the bigger area minus the smaller area. So the area is equal to, and I'm just going to keep it in fraction form. So 30 squared, 30 times 3 is 9. So 30 times 30 is 900 pi all over 2 minus, well, 5 squared is 25. So 25 pi all over 2. And since I kept it like that and I didn't reduce that first fraction, I now have a common denominator, so I don't have to worry about getting a common denominator. And I can think of those pi's kind of like terms. And so a 900 pi minus a 25 pi, this is equal to 875 pi all over 2. And we're in terms of inches squared. Okay.
Professor, I have a question.
Yes.
So from the first one, where did you get 30 squared, and then so you had to do 2 different
Areas.
Mm-hmm.
So the area of just like a pie shaped altogether, the area is equal to pi r squared.
Mm-hmm.
Right?
Okay. And then the 30
Oh wait,
inches.
I'm sorry, I'm wrong. It's r squared theta. It's r squared theta. Where am I off? Area is 1/2 r squared theta. So the 30, and so I'm wrong here, I shouldn't have pi. Instead of pi, I need to put in what I just had up here, what we found to be the radians. Okay, so I'm going to go back over here, and this pi should have been my theta. So it should technically be worth, or times 25 pi all over, over 36. Same thing here, this area for the smaller piece, it should have been 1/2 r squared times theta, and theta still is 25 pi all over 36. Okay. So 30 squared is 900. 900 times 25. That is 22,500. And this is 2 times 36. Oops, and we still have a pi. And 2 times 36 is 72. So then minus this piece. So 25 times 25, because 5 squared is 25, and then 25 times 25 is 625. We still have that pi piece there. All over 2 times 36, which is 72. So if I have 22,500 pi minus 625 pi, that gives me 21,875 pi all over 72 inches squared. Let's see, which is approximately, if you put that in the calculator, this is approximately 303.8 squared inches. So basically, again, if you were looking at your windshield of a car and you looked at this blade and it was swiping out while it's wiping, basically the piece that's getting covered or cleaned is in here, and that's what we just found. Okay, so now we're jumping into angular and linear speed. Okay, what is that? What is that talking about? So there's 2 things happening when you're rotating stuff. So if I'm thinking, let's say something on the point, if I'm thinking of a circle and I'm looking at the point on the circumference of the circle, I can think about how fast is that moving, that point moving as I go up and down or in a full circle. That is our linear speed. The other part is how fast is that angle moving back and forth, or how fast is that angle moving in a certain period of time, and that is the angular speed. Okay, linear speed we've worked with before.
I have a quick question before you move on.
Yeah.
On the previous problem, there was 2 numbers, 5 and 30. I was wondering where you got those from. Is that from the angles or?
5 and 30, yes. No, that has to do with the radius of the blade pieces. And so the radius of this whole blade, if I talk, or the whole arm itself is 30 inches. We were told that this piece though, right here, is 25 inches. And so that piece that is left, that is actually not being cleaned, is 5 inches in here, because I take my whole blade, which is 30 inches, minus off that rubber piece, which is 25. And so that piece that's not rubber, that's not getting our windshield wiper or windshield clean, we have to subtract that area off.
Got it. Thank you.
Mm-hmm.
Excuse me, Professor.
Yes.
What's the number that's under the 2,000 or 21,875 pi over 72? Is that the final answer?
Yeah. So if it wanted your, it depends on how my math lab asks for it. So if they ask for the exact answer, you're going to keep the pi and stuff in there. So sometimes they might ask for exact answer and then estimated answer. And so then the estimated answer, we would just plug that in the calculator and then round, and they will tell you in my math lab how far to round. So that would be, if I plug that in to the to the calculator. It's approximately 303.8 square inches.
Oh, I got a different answer.
Did you? Let me make sure. Oops. You know what? You're probably right. So let me try, because maybe I didn't multiply that by pi. 875 divided by x times. Yeah, I forgot to multiply by pi when I threw that in the calculator. So basically, if you take my answer right there, let me just rewrite that as 303.8 approximately pi, which if we multiply that out, we get 954 approximately 0.5 inches squared. Does that look better? Is that what you got?
Yeah, that's what I got.
Okay, great. Thank you for catching that. See, if I didn't have you guys here watching me, I could be misleading some people. Thank you. Okay, so linear speed is, well, remember our distance formula. Distance is equal to rate times time. If I wanted to find the speed, right, I could solve for r there. And so I could divide that equation, both sides by t, and I would get that the rate or the speed, r, is equal to the distance all over time. Okay, so instead of r for speed, like we've used in the past, we are now going to use the letter v, kind of like velocity, speed sometimes. So we're going to use v equals the linear speed. And distance. Well, if we're talking about an arc length, so that distance of the arc, remember we could find that, and that's what we're looking at. And the distance of our arc, so our distance is the arc length. And so remember, arc length was denoted by s, and that was equal to r times theta. So I'm just going to rewrite this a little bit differently. And so instead of the speed being r, I'm going to call it v, is equal to my distance, which is the arc length s, all over t. The s could be written as theta, all over t. So this is our formula for linear speed. Again, theta has to be in radians. Came up with some examples beforehand. Okay, so let me, before I do that, let's look at angular speed. So how fast is the angle moving? Okay, angular speed is going to be denoted with the Greek letter called omega, which kind of just looks like a W. So omega, the angular speed, is equal to theta. That's the distance of our angle that we have swiped across, all over t. Okay, I don't use this formula that I'm going to show you, but you can. I tend to just kind of stick with these that I know and how I can figure out. But we can convert our linear speed in terms of writing it with omega. So linear speed. Again, that formula we said was V is equal to R theta all over T, or S over T. Notice that this kind of looks like our omega function. We can rewrite this as R times parentheses theta over T. But by definition, omega, the angular speed, is equal to theta over T. So we can say that the linear speed is equal to our radius times the angular speed. Okay, so now knowing that, let's go through a couple examples.
Shouldn't the W be the omega symbol, or is that how it's written?
That's how it's written.
Whack.
Or am I doing the wrong symbol? Sometimes I get my Greek symbols off, but it should be the W one. Is that not called omega? Yeah, it's the lowercase letter omega. I don't know what the other one. Yeah, to me it looks like a W.
Oh, okay, gotcha. Thank you.
Yep. Okay, so let's say you just decided to go to the fair and you're looking at a Ferris wheel and you're trying to figure out how fast is that Ferris wheel spinning around. And you have some information and it tells you that the Ferris wheel has a radius of 30 feet. Okay, so example, we have a Ferris wheel. The radius of 30 feet. And you decide to pull out your phone and time how fast it takes one car on that Ferris wheel to make one full revolution. And you find that doing that one revolution, so I'm spelling revolution wrong. Takes 70 seconds. So what is the linear speed? Of the Ferris wheel? How fast are you going around in that circle? Okay, so V is equal to S all over T. Or S is R times theta all over T. Well, if you're making one full revolution, how many radians is that? Because our theta has to be in terms of radians. So if we have 360 degrees is one revolution, how many radians is one revolution?
Is it 2 pi?
Yeah, so 2 pi. So one revolution is equal to 2 pi. We have theta now in terms of radians. We know what our radius is. It told us it was 30. So the linear speed is equal to 30 times 2 pi all over the time it took, which is 70. And this is feet and seconds. So I notice my 10 goes into both of those. And so I have 3 times 2 pi, so this is equal to 6 pi feet all over 7 seconds. But if we put that in the calculator, we get back, that's approximately 2.69 feet per second.
Professor, you could just cancel out the zeros from the 30 and 70?
Yeah, because this is strictly multiplication. And so they both have a factor of 10 in common. If that was addition in between there, I couldn't do that. But if it's all strictly multiplication in numerator and denominator, we can cancel like factors.
Oh, okay.
Excuse me, Professor.
Mhm.
So, is there a difference between like seconds on a clock versus like the degrees, seconds and minutes?
Yes. Yeah, there is. The only, and it's a little confusing to me. But the only way I remember though what they are is because I know just about hours and minutes. Like there's 60 minutes in an hour, and I just think of that as 1 degree, but really 1 degree is not very far on, if you're looking at a rotation, right? 1 degree is just a little fraction. So I try not to think of it that way. I can look more into that and try to explain it better, maybe tomorrow. There was one other question for this asking us what is the angular speed? So that was like part A. Part B, what is the angular speed? Of the Ferris wheel. Well, omega is equal to theta divided by t. This is equal to 2 pi times t, or over t, which is 70. And if you plug that in the calculator, you get approximately 0.09, and this is radians per second.
Professor, is there like a certain formula that you would use? Like in this case, like if it's asking angular speed, you would use the omega?
Yes, so angular is with omega, the theta over t, and linear is the distance of the arc over t.
Oh, okay.
Okay, let's look at one more and then let's take a break. And this will be the last piece of 7.1. Okay, so now we're looking at a car, and we know the radius of a wheel of a car is 15 inches. The wheels are turning at a rate of 3 revolutions per second. So it's spinning 3 times in 1 second. How far is the car moving? Express your answer in inches per second and miles per hour. So we have a wheel on a car. And it's 15 inches. has a radius of 15 inches. And 3 revolutions per second. And so we want to know, how fast is the car moving? And what did I say? Inches per second? And in miles per hour. Okay, so inches and seconds isn't going to be too bad because we're given that the radius is in terms of inches and we're given that the revolution, that time period, is in terms of seconds.
Professor,
Yeah.
it doesn't say, oh yeah.
Sorry.
Okay,
Yeah.
how fast?
Yeah, so how fast is the car moving? So we know that the linear speed, denoted by v, again, is equal to s all over t. Well, s, again, is equal to r times theta. So if you want to write it like this, r theta over t. So we can pull out bits of information. We need to rewrite theta in terms of radians. So we are doing 1 full revolution, and so we know that that is 2 pi. So we have 2 pi times our radius, and we're given that our radius here is 15 inches, so times 15, all over the time. The thing is that the time is 3 revolutions per second. So I need to really multiply this by 3, all over 3 revolutions per 1 second. Because technically in that 1 second, it's gone 6 pi radians. So if I multiply that out, 3 times 2 pi is 6 pi, 6 times 15, that gives us 90 pi all over 1 sec. So if we do 90 times pi, this gives you approximately 282.7 inches that you're moving per second. So now we want to go from units that are in inches and seconds, and we want to convert it to miles per hour. And so kind of like we were doing yesterday when we were doing the degrees, minutes, and seconds, converting them, kind of like what we were going to do here, so that things that we know, units that can make 1, can cancel each other out. So let me just move this up. So we have 282.7 inches, and we have 1 second under here. So let's first convert inches to miles. Let's first think about inches and feet. So there is, and I know inches need to be in the denominator so it can cancel out in here. So I know that 12 inches, right, is equal to 1 foot. So I can put 1 foot divided by 12 inches. but I don't want feet, I want miles. So let's multiply this by what we know about feet and miles. So there are, and I had to look this up, 5,000, what, 5,280. So 5,280 feet need to go in the denominator to cancel with the feet up in the numerator. This is equal to 1 mile. So right now I've gotten everything into miles, but I'm still in terms of seconds, and I want this per hour. So let's multiply things that are going to cancel out the seconds and give us hours. Well, we know that there's 60 seconds in 1 minute. And I know that there's 60 minutes in 1 hour. So my units of minutes cancel, my units of seconds over here cancel. And so I would be left with approximately 282.7, all times 1 times 1 times 60 times 60 in my numerator, all over 1 times 12 times 5,280 in my denominator. And so if I multiply this out and I divide, I get 16.1 miles per hour. And it's approximate, so I should technically put not equals, I should use an approximation sign. Which is that squiggly equal sign. Okay, so okay, so we're getting into right triangles and pretty much the foundation of trigonometry. And so recall there's certain things that you need to remember about right triangles. So if we have a right triangle here, you usually denote that with a little box in the corner, and that's where the right triangle or the right angle is, which is 90 degrees. The side of the triangle that is directly across from the right angle is always the hypotenuse. And usually we denote that with a letter C, but it doesn't have to be. So C is equal to the hypotenuse here. I'm wondering if I make this bigger. Okay, and then legs. So legs are the sides of the triangle that is not the hypotenuse. So maybe an A here and a B here. So A and B are called legs. Of the right triangle. Oops. Okay. You guys probably remember, or if you don't, hopefully you quickly remember, and we'll use this all the time in this class, is the Pythagorean theorem. And recall that the Pythagorean theorem says if you square and sum each leg, this is equal to the square of the hypotenuse. I just want to make sure. So another thing that you guys need to remember is that the sum of all the angles in a triangle is 180 degrees. So it depends. Sometimes the angles are denoted with Greek letters. Sometimes the angles are denoted with capital letters. So a lot of times, notation-wise, the size of each leg and the hypotenuse are denoted with lowercase letters, and the angle across from the lowercase side is with a capital letter. Okay, so for instance, this is length A, and the angle across, directly across from this, that would be denoted with a capital A. And this is side B, that length is B, and so across from this angle, I'm sorry, across from, not that angle, that side, is angle B. Okay, so you might have remembered, or if you've taken trig before or some pre-calculus, you might have remembered the saying SOHCAHTOA. And that was a way to kind of remember what the trig functions represented. S represents your sine value. And so we're going to say that, and we write it as SINE, sine of theta. Well, that's how you say it, which we would write as sine SIN, and then the symbol theta. This is equal to, so notice that it has OH. So O is the opposite side. All over H represents the hypotenuse. Because I don't know if I hit something or if my computer's going crazy. Okay, so sine, here we go to back, is opposite of theta over hypotenuse. C represents cosine. So cosine of theta, I'm not going to write it out, but I guess I could. Let me just do it below, sorry. So shorthand is COS. And then you need to make sure that you put the theta there. If you don't put the theta there, it's technically wrong because it's of an angle. And this is equal to, well, the A is talking about the adjacent side of the angle theta. All over H is your hypotenuse. And then last but not least, well, there's more, but these are the ones that we can, if we know, we can get the other ones. And then we have tangent of theta. So TAN theta, this is equal to O is opposite of theta, all over the adjacent. Side. Okay, so theta, that's just representing the angle of the triangle. So let's look at a couple things with a triangle real quick. So you're clear what the adjacent and what is the opposite. So when we're looking at our trig functions, it's never of the right angle itself. It's of the other two angles. And so opposite, so if this is angle A, that would mean this is side A over here. Let's say this is angle B. So this would be side little b over here, and this is angle, or this is side C. So if I'm looking at cosine of angle A, so cosine is adjacent. So the adjacent side is the side, the leg of the triangle that is not the hypotenuse, that sandwiches that angle. So notice that hypotenuse is on one side of angle A, and then that side B is on the other side of angle A. Well, C is the hypotenuse, so the adjacent would be the side B. All over the hypotenuse, which is always, in this case, C. So cosine A is B over C. But notice, if we look at cosine from the angle of B, it would be different. So if I'm looking at angle B, right here, the adjacent side is the side that's sandwiching that angle that is not the hypotenuse. So the adjacent side of B is angle A, all over the hypotenuse, which is C. Sine of A, well, sine is opposite over hypotenuse. So looking at the angle, it's always the side directly opposite of that. And so from angle A, opposite is side A, little a, all over the hypotenuse, which is C. Where sine of B, this is equal to, so opposite would be little b of angle B, and then over hypotenuse C. So tangent of A, so that's adjacent over hypotenuse, I'm sorry, adjacent over opposite. So looking at A, adjacent is not the hypotenuse side, so it would be side B, all over the opposite. So opposite of A is side A. And then tangent of B, so looking at B, opposite is side B, and adjacent, oops, sorry, something's wrong. A is opposite.
Professor, did you say tangent was adjacent over opposite?
No, it's actually opposite over adjacent.
Okay.
So I was wrong on A, so good call. I was just noticing that. So notice A is opposite as A. Angle A is side A. All over the adjacent would have been B in here. And so tangent B, opposite is side B over adjacent, which would be side A. Okay, so let's look at an example where we're evaluating a couple of the trig functions using a triangle. So for example, let's say that we have a triangle that looks like this, where this is length 3 for one leg, and this is length 3 for another leg. and we're given this upper angle in this top of the triangle is theta. The lower left angle is the right angle, lower bottom angle, it just doesn't have a name. And we want to find sine theta, cosine theta, and tangent theta. Okay, so again, trigonometric functions, all it is the ratio of sides across from or related to a angle of a triangle, right triangle. The thing is, we're only given two sides of this right triangle, and so we need to figure out what that other length that is missing. And so a lot of times you're going to be doing this, and so you're going to be getting so fast of this Pythagorean theorem. So notice it's, in our case, it's the hypotenuse piece that is missing because it's the side across from the right angle. And so from here, then we know that c squared by Pythagorean theorem is equal to a squared, which is 3 squared, plus b squared, which is 3 squared. So we get c squared is equal to, well, 3 squared is 9 plus 9. So c squared is equal to 18. And c then is equal to, so you're using your square root method. We can take the square root of both sides. Usually you put plus or minus there, but right now we're talking about a distance, so we're not going to worry about that negative. So the square root of 18. Okay, so in this class, you want to make sure that you simplify your radicals as far as possible. You also don't want to leave radicals in the denominator. And so you're going to need to remember how to rationalize denominators. And so we can go through that in a second. But we can simplify the square root of 18 because there's a factor of 18 that is a perfect square, which is 9. So recall, you can break these down as a square root. 18 can be broken down as 9 times 2. I can pull out the piece that I can find the square root of. So square root of 9 is 3. I'm going to pull that outside of the radical, root 2. So we just found that c was equal to 3 root 2. Okay, so now that we know all the sides, the lengths of our right triangle, now we can apply the following. So sine theta, that was equal to opposite of theta all over hypotenuse. So if I'm looking at the theta, the opposite of theta, well, that's 3, all over my hypotenuse, which is 3 square root of 2. So we can simplify our fraction because we have both 3 in the numerator and denominator, and it's strictly multiplication between that 3 and root 2. So I would be left with 1 over root 2. So we want to get rid of that square root in the denominator. So we want to rewrite it so there's no radical in the denominator. And so in order to get rid of radicals in the denominator, we're basically multiplying this expression, which I like to call as a fancy 1. So we're changing it to how we're manipulating it how we want, but we're not really changing the value. And so I need that square root to fall away. And so I know square root of 4, that would cancel out the radical. And so I can rewrite this as, that fancy 1 as root 2 over root 2. So if I multiply straight across, I get 1 times square root of 2 is square root of 2, all over square root of 2 times square root of 2 is square root of 4, which is just 2. So sine of theta is equal to root 2 over 2. Cosine of theta, well, that is
Professor?
Mm-hmm.
So in this case, it wouldn't cancel out at all?
No, the 2 cannot cancel in the denominator with the 2 and the square root of 2 in the denominator because of that radical there.
Okay.
Yeah, good question. So cosine is adjacent over hypotenuse. And so if we look at the triangle, we're looking at the adjacent side. Well, that just happens to be 3, 2. Maybe I shouldn't have done this one first. All over the hypotenuse of theta, which is 3 root 2. We just did that work up here, and so I'm not going to redo it, and saw that that was just root 2 over 2. So let's say, oh, well, let's finish this problem before I go to that. Tangent theta. This was opposite over adjacent. So opposite of theta is 3. All over the adjacent of theta, which is also 3. So this is equal to 1. I'm going to come back up here and I'm going to see if I can grab our triangle, because I want to show you a couple things with what we just learned. I might be able to do this. Let's see. Yay. I'm so excited. That doesn't always work so nicely. So notice back at our triangle when we were looking at the relation of sides from an angle and those trig functions. So notice that some of those are identical. Notice this right here, this cosine of A is actually, look at that ratio, B over C. It's the same thing as sine over B. And then over here, notice that sine of A, we found to be side A over side C, looks identical to cosine of B. So that's actually not a coincidence. So there's actually an identity. How do you think you find angle A or angle B, knowing that we have a right triangle? We have a right triangle and we know that the sum of the angles has to be 180 degrees. What do we know about the sum of angle A and angle B? So angle A plus angle B, we know has to sum to be 90 degrees, right? Because all three angles we mentioned at the beginning of the section of a triangle has to sum to 180. So notice that I could rewrite angle A in terms of angle B. I can say, well, angle A then is the same thing as 90 degrees. I'm just going to subtract angle B on both sides, minus angle B. Or I could solve with the same equation we had, that angle A plus angle B has to equal 90 degrees. I can solve for angle B. So if I subtract angle A on both sides, I could say angle B is the same thing as 90 degrees minus angle A. Do you guys remember what it was called back in geometry when you sum two angles and it summed to 90 degrees? Those angles were called what of each other?
Complements?
Yep, so these are complements of one another. So recall, if two angles sum together and give you 90, they're called complementary angles. These are called complementary angles. So this cosine of A up here which is, as we said, was B over C, that ratio of side. Notice that this is equal to sine of angle B. Well, we just said that B could be written as 90 minus A. So we just said that this B value, I'm just going to go back in here and rewrite B with 90 minus A. So cosine of A, angle A, is equal to the same thing, sine of angle B, which is 90 minus A. So I can do the same thing, that sine of A. So if I look at sine of A, that was A over C up here. But the ratio sides of A over C was also cosine of B. So in general, I can say sine of A is equal to cosine. Well, angle B, we just, again, we can say is the same thing as 90 degrees minus A. I haven't talked about cotangent yet, so I'm gonna talk about tangent in a minute, but that also has a complementary theorem. So this is the complementary angle theorem. Okay, I want to give you, can get some theorems here that we're going to use over and over in this class. So recall, and I'm going to derive it for you, but recall by the Pythagorean theorem, if I took the square of the length of one leg plus the square of the length of the other leg, this was equal to the square of the hypotenuse. Well, let's say we went through this equation and we divided everything through by c squared. Because it's an equation, if we do something to one side, we can do it to the other and they remain equivalent. And so let's say we went through here and we took this equation and we divided everything through by c squared. And I'm going to rewrite that first fraction a little differently. I have a square in the numerator and a square in the denominator. So I'm just going to pull it out so that I'm squaring that whole fraction. So this is the same thing as rewriting it as a over c quantity squared. Plus, same thing with the second fraction. I'm going to pull that square out because it's identical as squaring both the numerator and denominator. So that quantity BC, quantity squared, is equal to, well, c squared over c squared is just 1. If you go back up to our triangle, though, let's look at that. What was a over c, which I have to go way up there, a over c. So my side, a over c, what was that? That is, I want to just stay with one of them, sorry. Let's keep with angle A. So A over C was sine A up here. And the B over C, so I'm going to rewrite A over C is just sine A quantity squared. B over C, if you went up here where the angle A, B over C was cosine of A. So going back over here. So this is equal to plus cosine of A, quantity squared. This is equal to 1. Okay, so just notation wise, normally we don't look at it written that way with a square outside of the trigonometric function like that, but that's what it means. A lot of times we write it where the square piece is after the sine and before the angle. So sine, S-I-N, then the square, and then the angle A. They mean the same thing. Plus cosine, quantity squared, angle A equals 1. So here's an identity that we are going to use over and over and over and again in this class, and it's going to be so helpful for you when you get into calculus to be able to identify this. So this is called a Pythagorean identity. Let me just make sure what they call it. Yeah. So this is the Pythagorean identity. You should also be able to identify or rewrite using this Pythagorean identity in different forms, because a lot of times in math, like we're manipulating things to make them fall out how we want them to. And so notice that if I solve for sine squared in that Pythagorean identity, I could subtract cosine squared A on both sides. Sine squared A, notice, is the same thing as 1 minus cosine squared A. So sometimes when we see that in an expression later on in the course, 1 minus cosine squared A, we can say, oh, that's just sine squared A, and replace it, and it will help us. Same idea, if I went back to this Pythagorean identity in this form and I solved for cosine squared A, basically I'd be subtracting sine squared A on both sides. So cosine squared A is equal to 1 minus sine squared A.
Yeah.
So let's say you had sine squared of 26 degrees plus cosine squared of 26 degrees. By this identity up here, what do we know that's equal to?
One.
Yay. So sine squared, same angle as plus the cosine squared of the same angle, so this is equal to 1. Okay, what about, here we go. So using one of the identities we just did, if we had 1 minus cosine squared of 15 degrees minus cosine squared of 75 degrees. So what are we going to get? Unfortunately, we can't add or subtract those cosine squareds because they're not of the same angle. Again, if we can manipulate this somehow using what things that we know. I noticed that either cosine squared or a 15 degrees could either be written as in terms of sine squared using that complementary angle, or I could do the same thing using the cosine squared of 75 degrees. I can use the complementary angle, rewriting that with sine. So either one would work. So let's just do the first one. So from that complementary angle, we could say that this is the same thing as sine squared of 90 degrees minus the angle of cosine, which is 15 degrees, minus the cosine of squared of 75 degrees. So this gives me 1 minus, well, sine squared, well, 90 degrees minus 15 degrees is 75 degrees. So we have sine squared of 75 degrees minus cosine squared of 75 degrees. And so to me, that almost looks like that Pythagorean identity of cosine squared plus sine squared equals 1. And I notice we can manipulate that to look like that by doing what to that expression? Well, I want this as be sine squared plus cosine squared. I want it positive sine squared and I want a positive cosine squared. So let's just factor out a -1 from both of those terms. So minus the quantity sine squared at 75 degrees plus, because I pulled out a negative, cosine squared of 75 degrees. So this is really 1 minus, and by the Pythagorean identity, same angle, sine squared of an angle plus cosine squared of the same angle is equal to 1. So 1 minus 1 is 0. Okay, quickly want to give you, there's 3 other identities, and they're basically the reciprocals of our other 3 trig functions that we know. If you can remember sine, cosine, and tangent, those are the ones that you always want to know. You can always get the other ones. So those are the ones I tend to memorize, and then I can work out, especially sine and cosine, I can work out the other ones. So there's what I call the reciprocal. Actually, that's not, yeah, okay. Reciprocal identities. So sine of theta, this is, or actually, forget it. Let's write it this way. Cosecant theta. Let me write it out first, and then we'll do the shorthand. So C-O-S-E-C-A-N-T. So C-S-C is shorthand of theta. This is the same thing as 1 over sine of theta. Secant theta. So shorthand is S-E-C, and then your theta. This is the same thing as 1 over cosine of theta. And cotangent theta, this is 1 over, I didn't write it out, 1 over tangent theta. and shorthand is COT. Another identity, not really the reciprocal identity, but one that you need to know. Is that tangent theta? This is equal to sine theta all over cosine theta. And I can prove that to you really quick, but we're running out of time. Let me just prove it real quick. So tan theta, this is equal to sine theta. Sine theta was opposite over hypotenuse, so O over H. All divided by cosine. Cosine was adjacent over hypotenuse, so A over H. So recall, if you have a fraction divided by a fraction, it's the numerator times, flip the denominator, fraction in the denominator, H over A. Notice now we have both the H in the numerator and denominator, those cancel. And this is equal to O over 8A. Sorry, O over A, which is opposite over adjacent, which is what our tangent theta is. So we proved that tangent theta is definitely sine theta over cosine theta, which means then that cotangent theta, if we wrote this as 1 over sine theta over cosine theta, and we invert multiply, so 1, our numerator divided by the reciprocal of the denominator, so 1 times cosine theta over sine theta, which is cosine theta over sine theta. So all of our trig functions can be correlated with sine and cosine. So you're going to be getting good, and we haven't really talked about finding the angles yet, of certain angles and knowing what that ratio of the sides would be. Let me see. Okay, so I'm going to stop there and take roll. And we pretty much got through of all 7.2. I do want to go over some more examples tomorrow at the beginning of class, but 7.1 and 7.2 are the sections that are going to be due by class time on Thursday. So by 10:15 a.m. to get full credit for your homework on my math lab, those 2 sections will be due. Okay, so I'm stopping the recording.